Hi everyone, this is Martin Shkreli in chapter 10 of chemistry. This chapter is called Liquids and Solids. Liquids and Solids. And I've prepared a nice little lesson plan here. This is an interesting chapter. It focuses quite a bit on a field called material science. Material science. And this is an area that I'm not particularly interested in, but perhaps it'll inspire some people to be interested in it. It still teaches a couple of concepts that are important relative to pharmaceuticals and medicinal chemistry. And this is the last, I'd say, probably the last theoretical chapter where we're going to have an important, sort of a couple of important concepts that you're going to need for organic chemistry. And after that, I think we're pretty much set on starting an organic course. I will go through the rest of the book, which is 22 chapters, and there is a preview of organic in here. But this is kind of the last important chapter as far as I'm concerned with respect to pharmaceuticals. I still think you should follow the entire lesson plan in the entire book, but at the same time, if I know some of you have limited time and you're only interested in learning about pharmaceuticals. There is part of the book part of this chapter that's a little confusing, and ironically, I had a visit from one of my favorite PhDs in chemistry, and I pointed the page to him, and neither of us could figure out what the authors meant by a certain piece of information. So it's kind of funny how we you could have an expert in the subject. My friend Steve is more of an expert than I am, and still not totally sure sometimes in chemistry. And I had another friend of mine, Matt, who's also a PhD in chemistry, and he said that the lessons he felt very well done, and says that he's seen people try to BS chemistry, and I'm doing a very good job. So thank you, Matt, for that compliment. And maybe I'll have one of these guys as a guest speaker in the show. So in any event, let's get to chapter 10, which is called Liquids and Solids. We all know there's three phases of matter: solids, liquids, and gases. And we spent chapter 5, I think, on gases. So we learned things like PV equals nRT and stuff like that. And one of the things that's important to understand about these three phases is we'll call these two phases, solids and liquids, the condensed states. Condensed states or condensed phases, because they really are condensed in terms of the particles that form in these phases, as opposed to gas, where the particles are really spread out in the gas, right? They're not so spread out in liquids and solids. So everything we can learn about phases, we can actually learn from water. We have water as a liquid, we have water as a solid, and we call that ice, and we certainly have water as a gas, we call that water vapor. The word vape has been very popular lately, so vapor is a good way to think of gas. Heat of vaporization is something we'll look at closely. So in any event, we certainly have different properties here, right? So solids are very dense, gases are the opposite. Solids you can't compress. We'll learn all about these properties. They're rigid, you can't compress. Liquid is kind of in between a solid and a gas. It's dense, it's not really compressible, but it does take the shape of its container, whereas others don't. So let's look at some of these interesting math, just sort of enthalpies that we'll have to sort of consider. So here's something we call the heat of fusion. And this is the amount of energy it takes to turn a solid to a liquid, or sometimes we call it melting, right? So say delta heat of fusion is FUS, fusion, is 6.02 kilojoules per mole. So it takes 6.02 kilojoules for every mole to melt every mole of ice into water. That's interesting. That doesn't seem like a lot of energy, okay? How about the heat of vaporization? That's to turn from a liquid to a gas, or to vape it, I guess, is something that people have been saying lately. So to evaporate a liquid into a gas, the delta heat of vaporization, literally like VAP there, is 40.7 kilojoules per mole. So that's 7 times as much as it takes to melt an ice, it takes to vaporize liquid water. So that's kind of interesting, right? Because it shows you that it takes so much more energy, and we're going to learn why. And interestingly, that covalent bond between the oxygens and the hydrogens to break those bonds will take just one of the bonds is half of this. So to break both bonds is 934 kilojoules per mole. So you can see that the strength that holds these things together, the forces, whatever they may be, and we'll talk about what they are in a second, the forces that keep the solid from becoming a liquid doesn't take much energy. The forces that hold the water as a liquid and prevent it from becoming a solid takes a little more energy. The forces that hold it being a water in any form, to break that down into hydrogen and oxygen, would take an enormous amount of energy, 50 times, more than that, 150 times as much as this energy, and 20 times as much as this energy. And I think that's a really important thing to understand. And this is a good segue into the first topic, which is intermolecular forces. And what we're going to find out is the first two are intermolecular forces, and the last one, this is an intramolecular force. And let me draw it a little more clearly. But the point is that the forces between the hydrogen and the oxygen in this molecule are intra, and that means within. It's within the molecule, intramolecular. But the forces between water molecules themselves, which we can draw below here and have more space, and we know that water does this, right? These sort of intramolecular forces, because we have these we learned about these dipoles, right? We have this partial positive charge here, and there's two partial negative charges here because of the electronegativity of the oxygen. So what you'll end up having is you have this sort of dipole attraction that looks something like this. And this is an intermolecular force. And intra means within, molecular. Intra means within, inter means between. The forces between molecules. And this is how these forces create different phases. So these intermolecular forces are responsible for something being a liquid or a gas, and I'll show you exactly how in a second. But these intermolecular forces are between molecules. And so even when water, this is really important, even when water goes from a solid to a liquid, it's still water. The molecule hasn't changed. The forces between the molecules may have changed. Same thing when water goes from a liquid to a gas. It's still water, it's still H2O, it's just maybe more dispersed. And the intermolecular forces have changed. So what are these mysterious intermolecular forces? Well, we learned one, the dipole-dipole interactions. We learned all about these, and I think it was chapter 8. Dipole-dipole attraction. And I just showed you a basic dipole. The oxygen is so electronegative, and the hydrogen is a little more passive. They're not sure that they want these electrons as bad as the oxygen. The oxygen really is hungry for these electrons. So these two electrons, you can kind of see them here. We usually omit this detail. You can kind of see them like this. And then oxygen has these lone pairs, these two lone pairs. Here are the 8 electrons that are being shared. Oxygen brings 6 to the table. Hydrogen brings, at least in valence, 1 to the table. So that's how we get 8. And you can see that these electrons are going to be unequally shared. This guy, because, I'm going to draw him in brown. Hopefully you can see the difference between brown and black. These two guys that are hydrogen's electrons, they're again, because the oxygen is so heavily interested in these electrons, it's so electronegative, that these electrons are going to kind of slide over a little bit. You know, sometimes when you're sitting with your sweetheart and you have your arm around her, or him, whatever it might be, they kind of slide in because they're attracted to you. That's kind of how oxygen is. It makes it slide in these hydrogen atoms slide into the oxygen. It's the main attraction. This oxygen is a stud, and the electrons will go over here. So without these electrons, the hydrogen just has this lonely proton left, and it's kind of got this partial positive charge. While the oxygen, it's got 2 nice new electrons that's kind of sliding towards it. So it's got 2 new negative charges. And we learned all about this already. But the point is that these are now dipoles. These are now dipoles. And these dipoles have their own attraction. So this is now positively charged hydrogen in a sense. It's kind of got this partial charge. And so what that means is it can attract a negatively charged dipole. And that could be something like a fluorine that's got a negative charge. It could be something like an oxygen that's got a negative charge. It could be any of the above, right? And the point is that there's sort of this intermolecular bond, intermolecular attraction between the molecules. And that's a dipole-dipole interaction, or dipole-dipole attraction. And now when you have hydrogen has really cool properties. And this is going to be really important. The hydrogen itself, when it forms one of these dipoles, we call that a hydrogen bond. And this is something that as a child confused me. What is a hydrogen bond? Because you would think it's like any bond that has a hydrogen in it, like this, right? Or maybe like this. But this, methane, these are not hydrogen bonds in the definition that we're kind of using. These are not hydrogen bonds in this definition. There are certainly hydrogen atoms bond to a carbon. I mean, they're certainly there. But this is when we say hydrogen bond, what we mean is a hydrogen dipole with a very electronegative. So anytime you have a very electronegative atom, like oxygen, very electronegative atom, let's pick oxygen or something like that, fluorine, I don't know. And you get a hydrogen dipole, that can form a hydrogen bond. And why is this so interesting? Why is this important? Why am I going through this? Yes, we're reading from the Zumdahl and Zumdahl textbook, which is my teaching tool, and we're on page 455. Why is this hydrogen bond so important? This is a important bond because most intermolecular bonds are not very strong. Most intermolecular forces are, let's just say 1%. 1% of a covalent, 1% as strong as a covalent or ionic bond. So they're not that important relative to the rest, right? And that's why when we saw here the heat required to fuse water is 6 kilojoules, and the heat required to vaporize it is 40, but the heat required, or the energy required just to make the bonds, the covalent bonds, are enormous. They're huge. But you can see here that you are getting somewhat strong. It's not quite 1%, it's closer to like 5% required energy. The point is that these hydrogen bonds are much stronger. They're the strongest kind of intermolecular force. They can almost be viewed as a bond themselves. So that hydrogen bonding is actually pretty important. We're going to learn more about it in medicinal chemistry and things like that. So anyway, London dispersion forces are the next force, intermolecular force we're going to talk about. That's the last intermolecular force we'll talk about. London dispersion forces. And actually, I have a funny story about this. When I had my old Xbox, not the Xbox One, but the Xbox 360, my screen name on that was London Forces. I thought it sounded, I played Call of Duty quite a bit. And Call of Duty is a game where you're like playing an army, basically. And I thought London Forces was a cool, most people don't say London Dispersion Forces, by the way. We can just say London Forces in chemistry. So London Forces are, I thought it was a cool name. It sounded like some mean army. And I used to play in that game, and I think it was a pretty good Call of Duty player. But anyway, let's talk about London Forces. So this is an interesting force. This is kind of mysterious. And basically what it is sort of this randomness that occurs in a molecule. Maybe the best way I can explain is let me pick a molecule like, I don't know, neon. Let's look at neon. Neon is the 10th Z number, right? Its atomic number is 10. It's the 10th one in a row. So we've got hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So it's the second Nobel gas. It's the first one with a completed p the two subs level, right? So the 2s and the 2p are complete. So you have 10 protons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is the nucleus, right? You have some neutrons in here too. You've got 10 neutrons that are interspersed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's the nucleus. That's easy. And so now in the first 1s orbital, we've got 2 electrons flying around, right? And the 2s orbital, we've just got the same. We've got 2 electrons flying around. And in the p orbitals, we've got 2 electrons flying around. Maybe the best way to put it is like this. This is a lobe. And so this should satisfy our octet rule, right? We'll have 6 of these p orbitals, 1, 2, 3, 4, 5. Haven't run out of room here, but there's one there. So you've got in the 2p orbitals, let's call this 2px, let's call this 2py, let's call this 2pz. And so this is kind of a neat concept. You have these very neatly drawn orbitals, but the reality is a little different. You know, these things aren't necessarily in these spots. They're moving around a lot. This guy could be moving this way, this guy could be moving this way, and say this guy could be moving this way. And what would happen if that was the case? What if I moved this guy from here, and I'm going to do it right now. And he happens to be, let's say, here, closest to his orbital edge, all right? And let's say I moved this guy from the far end of his orbital to maybe over here. And let's say I moved the S guy, who's here, and he can perfectly well be right here. So I'd have 3 electrons right next to each other, right? And what would happen? They would repel each other, right? They would definitely repel each other. But for a second, you'd have 3 electrons right next to each other. And this would be called as an instantaneous dipole. Instantaneous dipole, because the randomness from all the electrons, you never know where they're going to be. We learned about that in Heisenberg uncertainty principle, right? You never know where they're going to be. And here they are. Right now, there are 3 of them right here, all next to each other. And so this part of the atom is actually kind of has a negative dipole, right? It kind of does. It kind of does. I should draw my deltas a little better. That's a better delta. I'm making them like music notes. I learned too much music theory, I guess. And so the rest of the atom is going to kind of have a positive dipole, right? Because the electrons will kind of be over there, more heavily weighted over there versus more heavily weighted in the other direction. That's kind of what dipoles are. If you look at oxygen, they're kind of more closer to the oxygen. Yeah, this is elementary chemistry. We're trying to learn the basics, and it's very important to learn the basics first. I certainly know a lot more than this, but let's get through the basics, and then you can learn more advanced things. So in any event, these are what London forces are. They're instantaneous dipoles that result from the sort of random movement of electrons, and it sort of makes sense. Let me start a new page here. It sort of makes sense that the bigger the atom, and I'll think of that in terms of Z number, the more London forces you're going to have. And why does that make sense? Well, think about it. You have more of a chance if you have just hydrogen, 1 electron, one proton. There's not really a chance for London forces here. Now, of course, we're not going to see hydrogen in and of itself. So we're going to have a chance here with the basic covalent bond, the hydrogen gas. There is a chance that even within the molecule, you could have a situation like that, or you could have a situation like this, where it's kind of neither here nor there. Now we know because of the molecular orbital theory, we're going to have the bonding that's going to be generally in between the molecules. But you could have dipoles within molecules too that come from London forces. So think about that for a minute. So that's sort of it when it comes to theory. I think we're actually ready to get into organic. We're not going to, because the book, we're only about halfway done with the book, and there's a lot of other things we're going to talk about. But if you're just here for sort of studying medicine and organic chemistry, this is sort of it. I think we've gotten as far as we can get without getting into organic. We're going to learn a little bit more about other things, but we're pretty much there. The rest of this is relative to things like synthesis and things like solutions, stuff that we're not that concerned with at the end of the day in chemistry, for medicinal and organic chemistry, for drug designers and drug developers. But it's still important stuff, and I don't encourage you to skip it. But if you really have no time to study this stuff, I think that's kind of where I would stop. So anyway, we can talk about the liquid state. And so liquids are pretty neat, and they have all kinds of different properties. One of the properties we're going to talk about is surface tension. So liquids want a low surface area. Why? Because they want to minimize energy, right? So if you have these dipoles, think about the surface of a glass of water or an ocean or whatever it is. Here you are swimming in the ocean. This is water. Now, the water molecules, if you zoomed in really close, right, you'd have this dipole-dipole attraction, right? These are the intermolecular forces that keep this water, right? Otherwise it would be not water. Best way to put it. And so the point is this oxygen, interestingly, right, it sort of has nothing to interact with, as much as like this oxygen, which is making all of these bonds, these intermolecular bonds. So the molecule at the surface is only attracted to molecules below it. So what's interesting about water is that it'll form a droplet. Let's call this a droplet. And why will it do that? Droplet is a sphere, it's spherical. Why does it form a sphere and not maybe that or that? Why is it forming a sphere? Well, in math, what you'll learn is that the way you minimize surface area in any amount of a quantity is the minimal surface area is actually in a spherical shape. And so it'll minimize its surface area because it'll sort of fold itself into a sphere through its dipole-dipole interactions. And that's sort of what happens with water. And we're going to use this concept a little bit further. So one of the things that we'll learn is this concept of surface tension. Surface tension. And so this is the resistance of a liquid to increase its surface area. Again, liquids don't want to do that. They want the lowest surface area possible because increasing your surface area requires energy. It requires more energy. And we know because liquids form droplets that it won't do that. We know that systems tend to seek the lowest energy possible. So surface tension is the resistance of a liquid to increase its surface area. And some liquids, like water, are really resistant to doing that. But there's others that have lower molecular forces, lower intermolecular forces that have lower surface tension. So let's think about that. Sometimes you see the video of the lizard, little lizard guy. I don't know how to draw a little lizard guy, maybe like this. It's like a little dinosaur lizard guy. And he's hopping across the water, and they say it's because of surface tension. Because water has surface tension. You couldn't do that on liquid methane or something like that. A less polar liquid doesn't have surface tension because it has fewer intermolecular forces. Good example is methane. Methane doesn't have any dipoles. There's maybe slight dipoles here relative to H2O, where there's large dipoles. All right, let's move on. Let's talk about capillary action. Capillary action is the rising of a liquid in a narrow tube. So we've all seen this phenomenon. In fact, if you have a straw or something, you sometimes see this phenomenon. But if you have a glass capillary, the liquid will rise throughout it. And the reason that occurs is two forces, adhesive and cohesive forces. So the cohesive forces we've discussed. This is sort of the water sticking together through dipole-dipole interactions. But adhesive forces is interesting because the glass will often have different silicon, silicate, different atoms like this, which have electronegative species like oxygen and silicon. And the water will actually have dipoles, believe it or not, that will sort of be attracted to the different dipoles in the glass. And that's why when you look at a meniscus, there's actually, it looks like this. This is a meniscus. The curvature of liquid in a tube. This is the meniscus. And we're taught to read at the bottom of the meniscus, right? That's the reading we take when we say it's 10 milliliters or 15 milliliters. This is 10 milliliters. You don't read at the top of the meniscus, you read at the bottom. And this is because it's a polar liquid with high intermolecular forces. High intermolecular forces. So you get this attraction. It's trying to creep up. And that's, again, it has to do with the surface area. Viscosity is another property of liquid, and then we can move on from liquids. Viscosity is resistance to flow. It's like Jay-Z. Resistance to flow. He's resistant to other rappers' flow. That's viscosity. Just kidding, of course, but some liquids are very viscous, like glycerol. And glycerol is interesting. It's got this structure. It's got a bunch of OH groups, and you can tell they're polar. They're very polar OH groups. They form hydrogen bonds, in fact. They're that polar. So the point is that you're going to have a big resistance to flow. It's going to be sort of sticky, if you will, glycerol, because of these intermolecular forces that come from these dipoles. So that's what viscosity is. And high intermolecular forces is high viscosity, and vice versa, viscosity. All right, so let's get to some more trickier materials, and we're gonna kind of skip through some of this, and I'm gonna warn you. I promised you that I'll warn you anything we skip, but so I'll be doing that a little bit here. So this is about solids. We're gonna talk about solids. So we have two kinds of solids in basic terms. We have crystalline solid, and this actually has some bearing in pharmaceuticals. Crystalline and amorphous. And amorphous. And if you know anything about the etymology of words, this sort of means without order. You can have an amorphous, a politician can say something amorphously, or you can have an amorphous thought without order or structure. And crystalline makes more sense. So regular structure or order. What a mess. Regular order or structure. Amorphous without literally without morphology. Amorphous. Amorpheus, if you like those movies. Crystalline, sort of like a crystal, right? And so anyway, we think about these things in terms of lattice. A lattice. What is a lattice? It's a three-dimensional system of points. So if you think about a lattice of, I don't know, let's make a random molecule. We don't have to mark it what it is. This is a three-dimensional sort of lattice. Think about it like a dice as well, right? And these are atoms. Who knows what atoms they are? But let's assume they're atoms of something. I don't know. Let's just make this up. And pretty good drawing, if I do say so myself. So, in any event, this is sort of a unit cell. And a unit cell is the basic repeating unit of a lattice. So you can extend this into infinity. You could have a million of these. If you think about sugar or something, or salt, sugar actually doesn't form these, but think about salt, they'll form these huge crystals. And we think about this as a lattice concept. So one of the things we do a lot in medicine is we do something called crystallography. and sometimes we call this X-ray crystallography, or X-ray diffraction is what the book calls it. I call it crystallography. And in essence, we shoot wavelengths at these crystals, and we want to see how they bounce back. We measure that, and what we can do is we can actually divine the structure of the crystal. And this is extremely important. I'll show you a little bit of, I used to do this every day. Let's go to something called PDB. This is a repository. I'm going to paste this link. You can just Google RCSB PDB, and you can actually see crystal structures. These are complex and difficult, and they require enormous amounts of math. The book actually wants to get into some of that math. I don't think it's worth our time. So that's what we'll be skipping, is something called the Bragg equation. So if you really want to study this, you can read the Bragg equation. It's page 460 to 463. I think it's a waste of time, but if you really want to get into it, you could. I'd rather show you myself a little bit of the stuff. Let's pick an enzyme that I'm very familiar with. Pantothenate kinase is an enzyme I know extremely well. I invented some drugs around this specific kinase. So let's take a look at one of these drugs. This is the entry. There are always these 4-letter entries, so it's easy to do. And someone actually uploaded this. It's like free, it's like sharing, open source, if you will. And this comes from the E. coli system. E. coli is a bacteria that we use a lot in drug discovery. And you can see that this is the picture of the enzyme. You can genetically sequence this very easily. You can get a list of the enzyme's amino acid sequence. And this is a smallish protein. But what you can't do is use X-ray diffraction. What's difficult is to map out exactly how it folds. Exactly how it folds. Because that takes a very complex X-ray diffraction. And so here's what it looks like. And you can actually zoom in and mess around with it. Isn't that cool? And you can look up any protein. And here you have this is the protein and how it folds. And this is important because if you're a drug designer, you look at this so-called binding pocket and you say, this is the atom, the sequence of atoms, the molecule that will fit exactly into this protein. And that's why it's important, because if it's folding a different way, the drug that will fit in will be different. So if it's folding like this is the binding pocket, you need a molecule that will fit the binding pocket. This is a very simplified form. If it's folding like this, you need a molecule that will fit the binding pocket like that. And this is what drug discoverers like Steve and Matt, and to a smaller extent myself, do every day. You say, okay, I need a more lipophilic molecule. If this is lipophobic here, or hydrophilic pocket, I'm going to need something that's lipophilic here, or lipophobic here, more accurately. I need to sort of match it. You know, there's different ways that I need to understand how to pair off the molecules that I'm designing, and for that I need to do this X-ray diffraction. So this is actually really important, and instead of studying some of the formulas to do this, which I don't think will help you because they're way more complicated. They're way more complicated than the book is making it out to be. I don't think you'll get a lot of benefit from studying it. So I think I'll just show you some of the practical applications of it. So we're going to need this in medicinal chemistry. And this is the heart of drug discovery. The heart of drug discovery is crystallography. And sometimes we're not going to be able to take a crystal of a certain enzyme. A good example is 7-transmembrane GPCRs, G protein coupled receptors. They're very difficult to crystallize. Very difficult, if not impossible. There's some proteins that are too big to crystallize, like dystrophin. 3,000 amino acids. You can't crystallize something with 3,000 amino acids and hope to map it. Sometimes the resolution is low. This is a 2 angstrom resolution. This is very high resolution. But sometimes you have 7 angstrom resolution through something called cryo-EM. Cryo-EM, which is a electron microscopy. So with any event, this is the importance of crystallography. And I don't know what you're talking about, but crystallography is the core of medicinal chemistry. since I've actually made many drugs and crystallized many proteins. So let's move on. Page 464. Types of crystalline solids. The book starts to get on some tangents here, and we're gonna show you sort of how and why. All right, so there's a few different crystalline solids it wants to discuss. One is ionic solids. This is pretty simple concept, right? Extended lattice of an ionic solid like table salt, where you have ions you actually have ions at the lattice points. So here's an example. So lattice points will contain these ions. We know Na is the cation, and chlorine is the anion, of course. And so they'll kind of extend it ad infinitum, and that makes a lot of sense. Then we have molecular solids. Molecular solids. There was a cool little website that I found that I kind of need to use, because there's let me try to find it here. It's going to be useful. It's from Penn State. It's like Penn State chemistry notes. Here it is. And it kind of, I'll paste the link in here. They kind of do a good job of drawing a lot of this stuff, because I don't want to have to draw. I'm not a good enough artist. So here's a crystalline solid, and here's an amorphous solid. It gives you a good depiction of what I was talking about. You have a highly regular arrangement, and here you have kind of irregular, unpredictable arrangement. Same molecule. Here's the unit cell concept with the lattice point, the entire unit cell extending into infinity. And you have a couple of, and here, the book names all these: primitive cubic, body-centered cubic, face-centered cubic. I don't think you need to know that, to be honest with you. And here's a molecular solid. I was about to try to draw this, and it's better to just show you, where you have each point of the lattice is the actual molecule. And you can see here where they describe hydrogen bonds, and the actually distance between these is an angstrom, a couple angstroms. So all of this is pretty interesting. So you have molecular solids where instead of at the lattice point there's an atom, that's actually the lattice point is the entire molecule. And then finally you have these atomic solids, and these are probably the most confusing. And I don't think that it's that important. Again, I just had my friend who's a PhD in chemistry from a top university, who's many patents and drugs discovered. He was just over my apartment a few minutes ago, and we talked about how the book describes these atomic solids, and we don't think it does a fantastic job. We were both somewhat confused about these. So these atomic solids have actual just one atom. So a good example is diamond or graphene or buckyballs or fullerenes. These are all just carbon-60. And they're just repeating units of carbon. And these are sort of the most confusing of all. But in any event, we're gonna talk about that in more detail. So the atoms are at the lattice points. So in any event, for atomic solids like these, we have 2 or 3 kinds. So we have metallic atomic solids, like, I don't know, iron. Iron will form a metallic atomic solid, lots of iron, like an iron bar, right? An iron bar or a gold bar, right? That makes sense. Copper wire. And you have just a metallic atomic solid. And the kind of bonding we get, we're going to call this delocalized covalent bonding. Why? We'll show you in a minute. We're going to talk about how this happens. And this is the part of the book that we didn't like, where we called this a network solid. The kind of bonding we see here, we're going to call it directional covalent bonding. And the term we take objection to is the directional, and I'm not the only one that feels this way, but we'll talk about what that means as well, directional covalent bonds. And finally, we get the group 8A, aka noble gases, group 8A, the group 8A solids, which are the London dispersion forces. And you never really see this. This is kind of silly to even think about group 8A solids. You're never going to see neon as a solid unless it's basically at absolute zero. So I don't think it's that important. So let's talk about 10.4, structure and bonding in metals. And this is actually still very important, I would say. 10.4, metals. All right, so metals have interesting properties, right? They're very different. They have high thermal and electric conductivity. And we need to explain that somehow. Why are they so conductive? How is that possible? Conductivity, maybe. Okay. They're also malleable and ductile. They can be hammered into sheets or drawn into wires. And all of this comes from the non-directional covalent bonding. Non-directional covalent bonding. And we're going to talk about that. I keep teasing you. We're going to talk about it in a second, but we have to talk about something else first. And the arrangement that they form in these crystals we're going to call closest packing, which is the idea that we're going to try to get them into the smallest groups we can, using 3 dimensions and layers to get them into these groups. And I actually don't think this is important, but they go through these packing patterns. So hexagonal closest packing structure. We call it HCP. And then we have cubic closest packing, or CCP. I can't draw these because I'm no good as an artist, but they actually do a decent job here. Somewhere, hang on. Here we go. Which Penn State doesn't think it's too important to know, so I don't know that I do either. Let's see if we can find examples of closest packing here. I don't see it. Well, I guess I can try to draw one. So a good example is if we look at these molecules from the top, right? We have something that looks like this. This kind of looks like a hexagon, right? And these are all metal ions. And then on top of it, we're going to have, it's going to be slightly to the right. So a little pack on top of it. This is in 3 dimensions. And the next one will be packed back to the left, the next unit. So these are 3 units. And so forth and so forth. And this might confuse you and it's hard to see. This is how they pack on top of each other. The next one will be packed slightly to the right again. And this is a formation of packing. Then you can have them directly on top of each other. There's several ways to have these, and they're all named different things, and they all come out with interesting unit cells, and you can use these unit cells to calculate density. We're going to not do that. This is on page 466 and 467 if you want to, and 468. If you want to do all of that, you can. I don't think it'll get you anywhere. It's not too beneficial. And again, the Penn State folks skip it, and I would skip it too. So we're going to go to page 468. This is something you can't skip. We're going to talk about bonding models for metals. And this is really important. So we're going to go as slowly as we can here, because you might not understand it. So obviously we get these unique properties of metals, and we still need to figure out why that happens. The bonding in metals is both strong and non-directional. What does that mean exactly? It's difficult to separate metal atoms. That's why they're strong. Difficult to separate them, but easy to move them. Easy to move them as long as they stay together. So strong and non-directional. Now we're going to see that we have the opposite in the network solids where they're strong and directional. So anyway, how do we explain that? So we use something we call the electron C model. That's the most basic model. You probably learned about this in grade school if you studied chemistry in grade school. And the electron C model is this concept that the metals exist in this cation. There are these cations. And then you have a sea of electrons that are just kind of floating around within those, let's say iron. Here's the iron nucleus, right? Positively charged nucleus, it's a cation. And the electrons are just floating around it in a sea. And it's not really highly organized or structured. There's a sea of valence electrons, and the sea conducts the electricity. And that sort of makes sense. Of course, it's not a very sophisticated view. It's pretty how should I put it, elementary. So we have to get a more sophisticated view. And so probably one of the most sophisticated views we can do is we call this the band model, or the molecular orbital model for metals. It's a little more sophisticated, but not so much so that it's going to you're going to be unable to understand it. And this is the page 470. And the idea here is kind of neat. We basically think that the electrons travel around the metal in molecular orbitals formed by the valence electrons. So we have, one way to think about it is magnesium. So we have this kind of, book makes this drawing, it's kind of accurate and cool. You have this nucleus, right, 12 protons here. And the 1s is not going to be shared, it's too close. It's too close to the, here's another nucleus. It's too close to the nucleus. But as you get further from the nucleus, here's the 2s, here's the 2p, and here's finally the 3s. And it's sort of open for all of the nucleus to share. And the more cation nuclei you have, the more you end up not having one orbital, but really a band orbital. So all these orbitals merge. So the more, as n approaches infinity, as the number of atoms in this metal crystal approach infinity, the more interacting orbitals you have. All the orbitals kind of merge, and the electrons can flow freely around them at the highest energy level. That's what we call the molecular orbital model for metals. I mean, we're not going to get into tremendous detail. The book doesn't get into detail, and we don't have to get into detail, but that's something that's important. The book then talks about metal alloys. I'm going to skip these. I don't think you need to know the difference between all of these alloys. Again, this is material science. If you find this interesting, and it is interesting, you can certainly learn more about how alloys work. It's interesting for sure. Different kinds of steel. Chemistry has a lot of applications, as you guys know. I like the medicine application, but steel and chemicals or metals and chemicals are really important in our world. We need different materials, different plastics, different metals that are strong and have properties that we like. Cheap to make, biodegradable, all those things. That's what material scientists study. I think we're going to skip. It's about half a page we're going to skip, so but we'll be skipping more shortly. All right, now we're going to get to the kind of tricky subject that my friend and I don't love the way the book handles it. It's not terrible, but it's just sort of confusing if you're a very inquisitive mind. So we're going to talk about carbon and silicon, network atomic solids. And these are strong, directional, meaning that they're not going to move. This is kind of the curious word, directional. It means that unlike the metal, they can't move. They're rigid. They're in one direction. Not the boy band, but they're in one direction molecularly. So we call these network solids. They're brittle. They don't conduct, not conductors of heat or electricity. And that's the way they work. So carbon forms two kinds, it actually forms a lot of kinds, but two kinds we'll study are diamond and graphene. We all know what diamond is, and think of graphene as what's in your pencil. The gray stuff in your pencil is graphene. It's not lead. Might have used to been lead, but now it's graphene is the way people do it. So graphene is interesting. It forms these kind of interesting, we'll draw a typical benzene ring. And I'm trying to draw it in 3 dimensions, which is harder than it looks maybe. And then it sort of has layers. It's interesting, it has these layers. And there's obviously the covalent bonds between the benzenes, and then there's bonds that we learned about between the layers. These are non-localized, right? Pi bonds. And these bonds are sigma bonds. We learned that. So there's this weak bonding between these layers. In diamond, there's no bonding. They're all sigma bonds. This is graphite. Sorry, I'm saying graphene. It's graphite. Thanks for the correction. Graphite. I've got graphene on my mind. Graphene's very different. Graphite. Thank you for correcting me. Graphite is what's in your pencil. Graphene is very complicated. It's still a carbon network solid. All right. So one of the things that's interesting as to why they don't conduct electricity is we learned for the metals that you have this kind of close filled molecular orbital, and empty molecular orbital. This is what happens in that band model. And what happens in these network solids is that they're quite separate. So you can't shove extra electrons in the empty molecular orbital easily. It takes too much energy. That's why they don't conduct electricity. And that's why network solids don't conduct electricity. And I think it's obvious sort of why that gap is so large. All right, so the book tends to talk about all of these different materials. And again, I don't think it's worth learning. So page 474, you can learn about silica, which is SiO2, and a lot of glass and things like that in geology come from silica. So it talks about glass and pyrex, which is kind of a cool kind of glass. Then on 476, they talk about silica, which I also think is worth moving on from and not talking about. They talk about, ceramics and clays. Then finally on page 477, they talk about semiconductors, which is very cool stuff. I'm not saying that this is boring, semiconductors. I'm not saying this is boring at all, but the examples that they give aren't going to teach us much about chemistry, in my opinion. So we're going to move on to 2 very short sections where I don't even think they're worth being their own sections, but they have 10.6, which is molecular solids. We learned everything there is to learn about molecular solids, so I felt this recapitulated. A good example of a molecular solid is ice. H2O as a solid is ice, and intermolecular forces that form. Ionic solids, same concept. Ionic solids, like table salt, is the same concept. The only thing that they add here is they want to talk about trigonal, tetrahedral, and octahedral structures of ionic solids. I think it's beyond the scope of utility. I don't think that we're better off learning this. If you want to learn this, I think you would be wasting your time, but you can look at page 480 and 481. The book is addicted, and 482 for that matter. The book is kind of addicted to these morphologies and of these unit cells. I don't think that they're valuable to learn. Unless you want to become a material scientist, I don't think you're going to benefit from learning these. So let's go to the part where we do want to learn. And again, I'm always going to tell you when we skip stuff, so you can read it if you'd like, or you know what we're skipping at least. 483, vapor pressure and changes of state. All right, so certainly when something becomes a gas from a liquid, we have a name for that. We call that vaporization or evaporation. And to vaporize 1 mole of something, we love to name when you could vaporize 1 mole at 1 atm, or do anything to 1 mole at 1 atm, we call it, it's sort of a standard. And here we call that the heat of vaporization. Turning 1 mole of liquid at 1 atm into a gas is the heat of vaporization, or the enthalpy of vaporization, or we just say delta H vape. And this is a different unit for different things, as you can imagine, right? For water, it's very large relative to other ones, 40.7 kilojoules per mole. We did that in the introduction. And that's because of the high intermolecular forces, right? We learned about that. The hydrogen bonds create a high heat of vaporization. And remarkably, as you might be able to imagine, as a gas, there's these vapors have a certain pressure. And when that pressure, so if you take a thing of water, here's the water, some of it will evaporate, but some of it will come back down and condense back into the liquid, condensation. And eventually, the amount of vaporization and the amount of condensation will equal, and there'll be an equilibrium. We'll learn more about equilibriums in a future chapter. There'll be an equilibrium. And that pressure that's there at the equilibrium is what we'll call the vapor pressure. Vapor pressure. And you can measure vapor pressure with a barometer. And you can measure it in torr or whatever you like. And so there's, the book goes into, on page 485 to 488, goes into how to measure vapor pressure. And we are going to skip that because it uses something called a logarithm. And it's also very detailed, and I don't think it's very valuable. And I don't want to scare anyone with some math and complicated enthalpies of vaporization. You can just look them up. Measuring them, I think, is sort of a fool's errand. The only thing I'll discuss is sublimation. And sublimation is a simple concept where sublimation is when a solid becomes a gas. It skips the liquid, no liquid part. Usually you go from solid to liquid to gas. Here it just goes directly solid to liquid, or solid to gas. So I'm going to skip some of the vaporization calculations of vapor pressure. I don't think that we're going to benefit well. We're not well served studying that, taking logarithms and things like that. We're going to end up teaching more math than we're going to teach. We're going to teach chemistry, and I don't think that's too valuable. All right, so we're almost done with the chapter. I'm going to talk about briefly on page 488, changes of state. Changes of state. And a lot of this stuff makes a lot of sense. So heat of fusion, we learned a little bit about, but let's go over it real quickly. Enthalpy heat of fusion is just simply melting. And let's see what the heat of fusion is for some of these. So the melting point of oxygen gas is negative 208 degrees, the heat of fusion. For water, we know what that is. It's 0 degrees Celsius. That's the temperature where water is between, basically it's between solid and liquid, right? It's between solid and liquid. And then finally stuff like salt, to get salt to a liquid form, 801 degrees. So happy as an ionic compound that you're going to need that much heat to turn it from a solid to a liquid. And the enthalpy of fusion makes a lot of sense. This is 30.2 kilojoules per mole. This is 6 kilojoules per mole. And this sort of happens quite easily. It's 0.45, takes almost no energy, kilojoules per mole. So this makes a lot of sense in terms of heat of fusion. All right. Let's go to phase diagrams. This will be the last section, and this will be very brief. So phase diagrams are easier to use the Penn State phase diagrams. These are really useful, but they're really just a way to present information. So it's like a graph. You can read the phase diagram quite easily. They start with it as opposed to end with it. Let's look at a phase diagram. Here it is. Here's a classic phase diagram where you're graphing temperature on the x-axis and pressure on the y-axis, and you're basically showing as temperature increases, of course, we go from a solid to a liquid to a gas, but it's also pressure dependent. The higher the pressure, the more likely something is going to be, for instance, a solid or a liquid. At really, really high pressures, it takes a lot for something to be a gas. And you can see that going from a liquid to a gas is vaporization or condensation. That's an equilibrium concept. Same thing from solid to liquid. It's either melting and freezing, depending on what side you're on. And then sublimation and deposition are the two opposite signs of going from a solid to a gas. The triple point is interesting. This is where all three can coexist. At just the right temperature and just the right pressure, you're kind of flipping between a solid, liquid, and a gas, depending on whether you're increasing pressure or increasing gas. So all of these are best represented in a phase diagram. And this phase diagram is kind of neat, and it helps you be able to calculate a lot of these questions. So that's chapter 10. I'll give you a brief, really brief sort of introduction to chapter 11. 11 is going to be properties of solutions. We're going to breeze through this. We've been through now the hardest part of this book. We're about halfway done. This is page 510 to like 550 or so. In properties of solutions, we're going to talk about molality, which is a very important concept. That's going to be the kind of key learning. I'd say it's going to be molality. And we're going to be getting back into a little bit of stoichiometry. We're going to talk about solubility. That's going to be useful. And we're going to do, like I said, quite a bit of stoichiometry in chapter 11. And along the way, we're learning a little bit about chemistry in general. We'll talk about osmosis, different things like that. It's not going to be too bad. Chapter 12, so it ends at 551. Chapter 12 is chemical kinetics, and I skipped a bit of this when we went in the book and in sort of unorderly and non-recorded matter. So chapter 12, we're going to do it, and we're going to talk about rate laws. I kind of regret skipping it, but we're going to talk about rate laws, and this is basically all about reactions. All about reactions. That takes us to page 600. The book is nice, it's about 50 pages per chapter. Chapter 13 is similar, it's about equilibriums. We skipped this as well, so this will be new to some of you, and this is also basically all about reactions. And we have something called process chemistry that medicinal chemists are less worried about usually than process chemists, but I think it's important to learn it anyway. And that takes us to about 650. Then we get to acids and bases. Again, a lot of this is solutions, reactions. I think this will be relatively important, but an important chapter that'll get us up to 700. We have two chapters on acids and bases. So this is acid and base equilibria, titrations and things like that, buffers. That'll get us to page 760. Some of these are going to be pretty dry. More on solubility and ion equilibria. This hopefully gets us to 8. It's a short chapter, but it'll get us to about 800. Then on chapter 17, we learn entropy. So the important concept gets us to about 850. Electrochemistry, this will be relatively important. We get to page 880 or so, maybe 890. And then here's the final kind of important theoretical chapter is the nucleus. And we're going to learn about radioactivity and things like that. And I think it's practical to learn about this stuff. Then the rest of the book is kind of a survey. This is a survey of the representative elements. So it sort of starts an introduction to organic chemistry. And we're really starting to get to the end of the book here, since we're only about 1,000 pages. Page 970 is on metals and coordination chemistry. So we're going to learn some final theory here and understanding coordination numbers, which is going to be pretty important. We get to 1010. And the final chapter is a preview of organic. And we're going to launch into the organic course. So this will probably take us another week or two, is my guess. We just finished 10. So 11 to 22 is remaining. We're about halfway done. This has taken a few weeks, so probably a few more weeks, but we went pretty slowly on some of these complex theoretical ones. So now we're going to do some of these a little more quickly. These are a lot of stoichiometry, a lot of just hard work. So not much theory and learning, in my opinion. So anyway, thanks for joining, and I'll catch you all later.